In this virtual lab, I'm going to get you started on the exercise to study the law of refraction. So we're going to be using a simulation from the PHET group at University of Colorado at Boulder. So to get started, you can just go to your web browser and you can type in PHET, PHET .colorado.edu. Okay, so that'll open up the simulations, their main web page. Then you can say play with the simulation, and what we want is a physics simulation. So we can go here and select physics, and in the physics page you want to select light and radiation, and once you're there you'll select the one that says bending light. So if you click on that icon, okay, so this simulation can actually be run in your web browser. So if I just hit the play button, that will open up the simulation. And what you're going to do is you're going to run the intro. We're not going to use these other two. You're going to run the intro simulation. So what you'll notice in the simulation is that there is a flashlight. I can shoot the laser beam here. I can turn it off. And I can move this flashlight basically anywhere from 0 degrees to 90 degrees. Okay, so how do I know that there are 0 degrees and 90 degrees? Well, you can go grab this protractor and you can line it up with this normal line, this dashed perpendicular line, and that dashed perpendicular line is perpendicular to the interface between two media. So the two media that I'm starting with here are air, which has an index of refraction of 1, and the lower one, index 2, is water, which has an index of refraction of 1.3. I can change these indices of refraction. I can change it to glass, and you can see that the index has changed to 1.5, or there is a mystery index, which you'll be trying to figure out what the index of refraction is. There's a mystery B, and so, or you can customize your own, and with this slider you can change the index of refraction, and you'll see that number now is toggling as I move the slider button around. Okay, so to show how this works, I'm going to select water, and my flashlight now is in air. The beam of light is going to leave the flashlight, and it's going to hit the interface. There'll be a beam that is reflected, and then there'll be part of the beam which is now refracted, or basically bent, by the interface, and is transmitted into the water. So what you're going to do in this exercise is to move the flashlight around, changing the angle of incidence, which is the angle between the normal to that beam, and that'll also change the angle of reflection, which is the angle between this normal line to the reflected beam right here, as well as changing the angle of refraction, which is the angle of the transmitted beam with respect to that perpendicular line right here. So for what I want you to do in the lab, and I've given you written instructions, but this is kind of like a brief summary. So I want you to change this angle of incidence, see how it changes the angle of reflection, and see how it changes the angle of refraction. So as a kind of a test, I could put this at, say, 30 degrees. So my angle of incidence now reads 30 degrees. My angle of reflection reads around somewhere between 29 and 30 degrees. So I'm just going to round up and say 30. You'll notice that the protractor has increments of 1 degree in it. So that's the precision that you'll be able to use. And the angle that's refracted, the beam of light has refracted to, is 5, 10, 15, so about 20 degrees. So there is going to be a certain amount of error involved in your measurements, in the fact that the precision that we have with this protractor is only down to 1 degree, and you can't really enlarge the protractor. The protractor is just the size that it is. So you kind of have to read off and, take into account what the tolerances are on the readings on the protractor. So for the experiment that you're going to do, you're going to measure 5 different angles of incidence, measure the 5 angles of reflection and refraction, do that for air and a water interface, and then analyze the data, basically plot the data on a graph, and then try and extract what the index refraction is for water. And hopefully it'll match what the simulation is using for that index. So then you'll switch to mystery material A, repeat, so do 5 angles of incidence, see what the angles of reflection and refraction are, analyze the data, and now extract what is the index refraction. Repeat the whole process for mystery material B, and then that should give you a good indication of what, of coming up with a law for the how the law of reflection, the beam of light that gets reflected, as well as a law of refraction. So after you've done that, the last part of the lab that you'll do is switch this around such that the material number 1 is, say, glass, and the material number 2 is air. And then you want to find what's called the critical angle. Essentially the angle that when you turn it, you no longer have any transmitted light and you only have reflected light. So we basically just read off this angle of incidence, and that will be your critical angle, the angle where you have no transmission into the air. So how do I know? Well, I mean, I don't see a beam of light that gets transmitted. The other interesting thing about this simulation is it does have an intensity meter. So I can read and say 100% of the light comes out of the flashlight. And then if I move this and go over here, 100% of the light is now reflected. If I now see there is an amount of light that is transmitted, I could actually say that about 58% gets transmitted and 42% gets reflected. So once you reach the critical angle, now we're down to almost at the critical angle. Now we're at about 17% has been transmitted, 83% gets reflected, and so the whole point of the critical angle is that now 100% of the light gets reflected back. So those are the tools that you'll be using. So this is what you're going to use for your data collection. And like I said, the actual instructions on how to perform the lab are written out. And so you can follow those instructions. So good luck.